The last part in this chapter are percent compositions and combustion reactions and some calculations with them. The good news about chemistry and percents are no different in chemistry. It's always part divided by total times 100. Parts in 100, right? And so what you can do if you have a, let's say you have a 7% sodium solution. That means that there are 7 grams of sodium in 100 milliliters of solution. You can use this as a conversion factor. You don't necessarily have to use the formula part divided by total times 100 and solve. You can, and that's fine. But this can make it easier. Or if you have sodium chloride and you calculate, and I'm making this up, I'm guessing that 43% are sodium in sodium chloride. That means that there are 43% sodium in sodium chloride. That means that there are 43 grams of sodium equal to 100 grams of sodium chloride of total, right? Here's the total, and this is your part. And if I ask you how many grams of sodium are there in 450 grams of sodium chloride, you can say, okay, there are 450 grams of sodium chloride, and you use this as a conversion factor, right? You write there 100 grams of sodium chloride, and 43 grams of that are sodium, and you get an answer. Or if I say, how much total do you need, how much sodium chloride do you need if you need 50 grams of sodium, you can also start with 50 grams of sodium, and then all you have to do is reverse this conversion factor. You divide by 43 grams and multiply by 100, right? So the sodium grams, sodium cancels, grams of NaCl. You can work a conversion factor method. Sometimes it's a little quicker. Okay, so let's take a look at a particular specific example. We're going to calculate the composition of sodium nitrate, and all you have to do is go to the periodic table, look up the molecular weights, calculate the atomic mass units for sodium nitrate, do the same thing for each of the components, right? We have 1 sodium, we have 1 nitrogen, you multiply that out here. 3 times oxygen, you get the parts here. This is part oxygen, and then we have total. And then to get the percents, you take the part, you divide it by the total times 100, as shown here, right? So percent sodium, 22 part divided by total, 84.99 equals 27.05% sodium. And we get conversion factors for that, for these then as well. If I ask you something related to sodium and sodium nitrate, you use 27 grams is equal to 100 grams, right? Okay. So if I ask you a question like how many grams of oxygen are contained in 257 grams of sodium chloride, you use the conversion factor that relates the grams of oxygen to the total grams of sodium nitrate, which is of course 56 grams. 0.47 grams of oxygen equals 100 grams of sodium nitrate. Okay, so let's do that. So then you have 257 grams of NaNO3 times, we use that 56, oh, where did it go? 56.472 grams of oxygen divided by 100 grams of sodium nitrate, and the answer is 145 grams of sodium nitrate. Now alternatively you can use the percent, but this works just as well, right? And so how many grams of sodium nitrate would contain 27 grams of sodium nitrate? So you have 27 grams, 0.5 grams of sodium. You look at the sodium conversion factor, which was, okay, let me go back and look. It also is 27, so okay, so it's 27.05 grams equal to 100. So here we have 27.5 grams of sodium. So it's really going to be close to 100 times 100 grams of sodium nitrate divided by, and the 27 here, 0.048 comes from the part, and that's going to be 101 grams. Okay, and of course you can also say part divided by total. That would be 27.5 grams divided by 0.27048% equals 101 grams, right? So I took the percent and I turned it into a percent fraction. So even here, part divided by total times 100, I cut corners instead of taking 27.084 and multiplying by 100. And whatever gets you the result. Okay? So now we can do some neat little problems determining the empirical formula with percentages and the molecular formula. Just as a reminder, we already know what that is. For molecular compounds, it's the smallest ratio. We had an example of C4H8 where you could divide, there's a common factor, so the molecular formula is C4H8 and the empirical formula is CH2, and so the percentage for both of those is the same. So you can, if you're doing a percent composition, you are doing it for the empirical formula, and you're going to need a little bit more information to go from the empirical formula to the actual formula. So you're going to need to know the actual mass of this compound, or you cannot do it, right? For ionic compounds, it's the same. It is already reported as the smallest ratio here. NaCl is already the empirical formula. Basically, it's in a 1-to-1 ratio. Okay? And so just as a reminder and to practice, if I ask you for the empirical formula, it's kind of an easy question for any of these. These are all ionic, metal and a nonmetal, metal and a nonmetal, metal and a polyatomic ion, that's ionic. They already are in their empirical formula. For molecular formula, which are covalent compounds, you find the common factor here. You can divide both of these by 6. So CH, so C6H6, which could be benzene, could be something else, has the same chemical composition as acetylene, which is C2H2, which also has a empirical formula of CH. So those are the same. Here we have C12H24O12. You can divide that by 12, 12, and 12 to get CH2. So that's the empirical formula of that. Okay. Alrighty then. Empirical formula for masses of elements. What is the empirical formula of aluminum fluoride? A sample, hang on, oops, alright, sorry. What is the empirical formula of aluminum fluoride? A sample of the substance was analyzed and found to contain 1.3491 grams of aluminum and 2.8498 grams of fluorine. Okay. This is not a great question because it's an ionic compound, and if you know anything, you know the answer without looking at it, because aluminum is +3 and fluoride is -1, so it's AlF3. Problem solved. But if I didn't tell you it's aluminum fluoride, or if I told you an ionic compound containing a cation and an anion, then you don't know. Could be just about anything. No, that doesn't work. I'm going to have to give you aluminum and fluorine. So let's just keep ignoring that we know the answer and do the calculation anyway, right? So you just calculate, you can calculate the parts here. You calculate the number of moles. So you can take 1.3491 grams of aluminum times 1 mole of aluminum divided by 26 from the periodic table, 0.9815 grams of aluminum. That gives me 0.500 moles of aluminum. That's how many moles of aluminum we have. Okay? And if this is going to be in the 1 to 3 ratio, then if I had to guess, we're going to need to get 3 times as many moles than that. So then the answer here should 0.1500 moles of fluorine, if this is correct. But you want to do the calculation, and so here we have 2.8498 grams of fluorine times 1 mole of fluorine divided by, go periodic table, look up what it is. It is 18.998 grams of fluorine, and it does indeed give you 0.1500 moles. Okay, so this works out really neatly, but so what you want to do is you want to take the larger mole and divide it into the smaller. So you take 0.1500 moles of fluorine divided by 0.05, which of course is going to be 3. So this is in a 1 to 3 ratio, which confirms what we had already. Aluminum fluoride is AlF3. I could give you something that's not that straightforward. You can take a good educated guess, but you're still going to have to do the calculation here. What is the empirical formula of potassium permanganate? This substance contains 24.74% of potassium, 34.76% manganese, and 40.50% oxygen. Alright, so the trick here is, and I'm not going to give you this hint for an exam, to basically assume 100 grams, which means we have 100 grams. That means we have 24.74 grams of potassium and 34. See, I'm avoiding and so on and so forth here because you know what? I'm going to eliminate this bonus point thing at this point, right? Because I like saying and so on and so forth. So no more bonus points. All right. So then what we do is we take the grams of each of these, right? So we take the 24.74 grams of potassium times 1 mole of potassium divided by 39.098 grams. That gives me 0.622 moles of potassium. I do this with manganese now. 34.76 grams of manganese times 1 mole of manganese divided by 54. Hang on, is that what it is? Yes, 54.938 grams of manganese gives me 0.6327 moles of manganese. That's roughly 1 to 1, so that's good to know. And then we have 40.50 grams of oxygen times 1 mole of oxygen divided by 16.00 grams of oxygen, and I get 2.53 moles of oxygen. Okay, so you take the larger, just take the larger, 2.53 moles of oxygen, and divide it by one of these, 0.632 327 moles, and you actually end up with 3.99, which is a 1 to 4 ratio. So this is in a 1 to 1 to 4 ratio, which means it's KMnO4, which unfortunately, again, I wasn't truthful here. You could have figured out by knowing what permanganate is, MnO4, knowing it's -1, and potassium is +1. Okay. All right, what if I give you a molecular compound? Okay, and in order, you can calculate the empirical formula if I give you percentages, but if I don't give you the molecular formula, you can molecular weight or the molecular formula, you can't take it any further than the empirical formula. But if you know both, it's simply then a ratio of the two, right? So if you have the molecular weight, which is 360, and it has so that's going to be some sort of factor of that, times 3 or times 4 or times 18. We're just trying to figure out how many times 360 fits into our empirical formula. So if I divide that by 30.02, I get a ratio of 12. Okay, so that means I have to multiply this by 12 to arrive at the molecular formula. So this is C12H24O12, which is sugar, table sugar, disaccharide. So you get the idea, right? And so a formula like this, an alkyne with a molecular mass of 54.09 grams, was determined to have 11.18 grams of percent hydrogen, and 88% carbon. So we have two components here. We have carbon, CX, and HY, and we want to know what X and Y is. Okay, now you can do what we did before. You can say you have 11 grams of hydrogen and 88.82 grams of carbon, and you can convert that to moles and look at a mole to mole ratio. And then, but you can, since you are giving a molecular weight here, right? You should actually apply that. It's a little bit. It adds a step, but it helps you with your mole to mole ratios. So either way you do it, I'm going to do it with the applying the percentages to the grams. So, and that's going to make my mole ratios work out without having to figure out what is the ratio. Okay, it's going to make them work out perfectly. So if I have 54.09 grams of this CXHY and 0.1118, 11%, so I already divided by how, that's a percent fraction. Okay, I end up with 6.047 grams of hydrogen. And if I convert that to moles, 1 mole is equal to 1 gram. I end up with 6.00 moles of hydrogen. And so I already know that Y is equal to 6. Because I don't have to worry. I no longer have to worry about the mole to mole ratio. If I don't give you that, you can't do that. You have to use 11 grams. Okay, so I do the same thing with carbon. 54.09 grams of this stuff has carbon. So that's times 0.8882, so 88%. I end up with 48.04 grams of carbon, converting to 1 mole of carbon divided by 12.011 grams of carbon. I end up with 4.00 moles of carbon. I don't have to worry about the ratio. I know that this is C4, that's going to be the molecular formula, C4H6. Now, let me read this real quick. I also want to know what the empirical formula is. So I do need to divide this by 2, which is C2H3. That is the empirical formula and the molecular formula. Okay. Alright, so looking at another percent calculation. Here we have a hydrate, barium chloride, but it is mixed with sodium chloride. So I have so a student has a mixture of barium chloride, which is a dihydrate, and sodium chloride, and he heats the sample until the mass did not change. Okay, the reason he heated is to determine the mass of grams grams of water in this hydrate, because this will come off upon heating. Barium chloride will stay behind and sodium chloride will stay behind. So here you have an empty crucible, and you add your sample to it. So the difference here is the total sample with sodium, barium, and water, which is 2.814. When you heat it, you're driving off the water. So 0.168 grams of this is water. Okay, so the game plan here is, now we can figure out how many moles of water were there, right? So 0.186 0.168 grams of water times 1 mole of water divided by 18.01 grams of water. That's going to give me the number of moles of water. And I know based on the number of moles, for every 2 moles of water, there's 1 mole of the entire hydrate. So if I now figure out you can now, so the grams of water cancels, and this is moles of water, and so there's 1 mole of barium chloride times 2H2O for every 2 coming right from there moles of water. That will give me the number of moles of barium chloride. And then I can actually determine the mass of barium chloride and subtract that from the original mass to see how pure it was. Does that make sense? So you calculate the molecular weight. Now you have to add in those 36 grams of water. But if you do that, 1 barium from periodic table, 2 chlorines, 4 hydrogens, and 2 oxygens, you add it all together, you get 244.233 grams of hydrate. I'm going to call it hydrate, or hydr, because I'm running out of space, divided by 1 mole of hydrate. I get a mass, and that's 1.140 grams of barium chloride times 2H2O. So roughly half of that original sample was hydrate. The rest was some other stuff, right? So calculate the percent hydrate in the original sample. So all you need to do is part 1.140 grams of hydrate divided by the total, which is 2.814 grams of total mass, times 100 equals 40.50% of this stuff. Okay, so you gotta just practice some of these problems and work through it. Alright, so some really cool problems involve the combustion of hydrocarbons. And hydrocarbons contain either just carbon and hydrogen and oxygen, or just carbon and hydrogen. Okay? And so we can burn them. We know that when we burn a hydrocarbon, okay, something that has carbon and something that has hydrogen, and there's a bunch, right? There's propane and butane and methane, and you burn wood and paper and whatnot, and so there's some oxygen in some of these other ones. But you can burn these. You set them on fire, and what happens? They react with oxygen, and this will always produce the same products. All right, it's going to produce water and carbon dioxide. Of course, you never observe the water. Carbon dioxide is a gas, and the water goes off as a gas because the combustion is so hot. So you're just basically burning, let's say you burn a piece of wood, and you end up with just a bunch of soots or just some residue. But if it's a propane gas, you get a clean combustion. You just need to feed it oxygen. Okay? And so what that means is that if you can capture the products and weigh them, you can determine the number of moles of water, and you can determine the number of moles of carbon dioxide. And let me go to the next page, because I'll explain it there, right? So you can actually, if you burn it in a furnace, and you have plenty of excess oxygen here. And so here you have this compound, CXHY. Every single one of these hydrogens is going to be captured here in the form of H2O. So you end up with, for every 1 mole of H2O that you produce, you had 2 moles of hydrogen in the original compound here, right? Because it takes 2 of the originals and makes 1 mole. So for every 2 moles of hydrogen in the original sample, you make 2 moles. For every 2 moles of hydrogen in the original sample, you make 1 mole of water. And the same is true for carbon dioxide. Not exactly the same, but it's 1-to-1 because there's 1 carbon. So for every 1 mole of carbon dioxide, you had 1 mole of carbon in the original sample. And then you can backtrack and look at the molar ratio, right? You see how that works, right? So all of the original carbon forms carbon dioxide, and all of the original hydrogen forms water, and they are in a distinct ratio. Now let's do a problem here, and this one is worked out, so I'm not writing on the screen. But if you have, upon combustion, a compound containing only carbon and hydrogen. Combustion means, okay, we burned it, right? So we took this, it's the same thing. It's CXHY and O2, and we don't know how much O2 we have. There's just an excess there, so we make sure it burns and goes to completion. We form CO2 and H2O. Alright. It produces 1.83 grams of carbon dioxide and 0.9101 grams of water. Alright. So first you calculate. Okay. I kind of wish. Okay. Let's just follow this. Alright. So you take the grams of carbon dioxide, and you calculate based on the molecular weight of carbon dioxide the number of moles of carbon dioxide. And that's actually going to be equal to the number of moles of hydrogen. Carbon, of course. 0.0416 moles of carbon, because it's 1-to-1. There's 1 carbon incorporated, but here it's 2. Alright? So if I do this for hydrogen, this is not, you're going to have actually double that, or 0.100 moles of hydrogen in the original sample here, right? So that's what this is here, right? So for every 1 mole of carbon dioxide, you had 1 mole of carbon in the original sample. So we have 0.0416 moles of carbon. For every 1 mole of water, we have 2 moles of hydrogen in the original sample. So you multiply that by 2, you get that 0.1 moles. And then you look at the ratio, right? So you take that, hey, they didn't do the ratio. Oh no, they simply put those are the mole to mole ratios, right? So you divide, okay. So then you divide the largest into the smallest. Of course, carbon gives you 1, and if you divide 0.1 by 0.0416, you get 2.4. And then you play a game. You multiply that by 2 and see what happens. So if you multiply that by 2, you get C2H 4.8. That's not good enough. Then you multiply that by 3 and you get C3 H H7.2. You're looking for something whole. Then you do this with 4, and you end up with C4 H9.8. And you do that with 5, and then bingo, you get a result. If you do that by 5, you get to C5H12. Okay? So this is your empirical formula. You don't know the molecular formula. This is just the empirical formula. Now, these problems are great. I encourage you to work a few of these, right? Here's another example. It's the same thing. You have upon combustion containing only carbon and hydrogen. So again, you calculate the moles of carbon dioxide, and so they are 1 to 1, and then you calculate the moles of hydrogen, and then they're 1 to 2, and then you look at the mole to mole ratio, and you come up with an empirical formula. Okay, so I love those problems. Love them for the exam. This is the end of chapter 4. This was a long one, 32 minutes. Hopefully you're still alive. Good luck for the exam.